Greetings. Our senior design project is titled the FibTech Mechanical Human Thorax Model for Automatic and CPR Device Testing. We are Team 19, which consists of Nader Kasem, Zachary Briggs, and Haley Parsons. Our faculty advisor is Professor Kumavor, and our sponsor is the FibTech LLC. Some background information on our sponsor, the FibTech. They are an award-winning company designing resuscitation equipment for public safety, as well as lay people and industrial use. They design and manufacture automated external defibrillators, also known as AEDs, mechanical chest compressors, and related accessories. Two of their products can be seen to the right. They have had more than 450,000 AED units shipped worldwide and are headquartered locally in Guilford, Connecticut. Some background information about the human thorax model and our drive to make a more accurate and efficient device. Cardiac arrest often results from cardiovascular disease or myocardial ischemia, which is a lack of blood flow to the heart, and is the leading cause of death in the world. Early CPR intervention drastically increases the chances of survival and limits neurological deficits resulting from hypoxia. So even if the patient is successfully revived, there's a high probability that if their brain has been deprived of oxygen, that they will have long-term neurological deficits and possibly be considered brain dead. When compressed, the human thorax has a unique nonlinear behavior that is often poorly represented in current training devices. Therefore, our team is striving to design a thoracic model that accurately represents human chest biomechanical behavior to improve responder training and CPR assist devices.
Our problem statement. The mannequin for CPR training used today is not an adequate nor accurate model of an actual human chest. The human chest contains organs and tissues, and this causes the chest to recoil more than that of an empty foam dummy. There must be a device implemented that will provide the recoil and dampening effect into the CPR mannequins. The design of a new mannequin with a dampening effect, along with other changes to produce a more effective training program and device, is needed to appropriately train regular people and first responders on CPR. Some components that we implemented into our prototype are an ultrasonic sensor, a force sensor, and a stepper motor. SolidWorks. There were a few changes that we made since what we wanted for our design a couple months ago. As you can see in the old version, the middle and bottom pieces are bigger in diameter. They were also kind of combined. There was housing for an accelerometer and no housing for the force plate. In the new version, the bottom and middle plate are completely separate components that you can put together. There is a coupler that has the correct shape for the top of the stepper motor to turn it. That was a huge issue with last year's group. For the top plate, as you can see, there's the housing for the force plate, and there's a top part of the top plate, so that way the force plate can fit snugly and not be affected when pushing down on the entirety of the top plate. Our 3D printing process. Here are some images of our prototype fresh from the 3D printing place. It is exactly what we hoped for in size and height. We do have to kind of sand down a little bit and then re-drill in the holes, but other than that, we're just waiting on 2 more components that are still 3D printing.
When plotted, the force displacement curve should show a linear compression and a non-linear decompression. This figure shows data only from the ultrasonic sensor to see how the data would be plotted. Once we collect more data, we will compare that graph to the human thorax model. Due to time constraints, we did not have the opportunity to test the device using different materials. Future work for this project might include testing the fabrication of the device using different materials in order to improve the weight, durability, and cost of the device. During this project, we focused mainly on the functionality of the device. Therefore, it is currently too big to fit inside of a CPR mannequin. Going forward, we would like to make the device smaller so as to fit inside of a proper CPR mannequin without sacrificing the functionality nor the structural integrity of the device. I would like to end this video by thanking our sponsor, DefibTech, our faculty advisor, Professor Kumovar, our TAs, and UConn's very own School of Engineering for their hard work and support during this project.